microstructure characterization from a data analysis perspective.
Yes, thank you, Dick. So this talk is going to be about how to kind of analyze these data we get out of, for instance, FIB-SEM. So it's not going to be much about kind of the consequences of these measurements you get out of it, but how to kind of obtain these measurements. And also I'll talk a bit about how far we are in the process of actually automating this entire process of obtaining data and achieving some measurements in the end. So just a brief overview of my talk. I was asked to give a very brief introduction to fuel cells because I heard that some of you might not actually have a background in fuel cells. So I'll do a very, very brief introduction to fuel cells. And then I'll go on to going through our pipeline, how we get from a series of images to actually be able to obtain some three-dimensional measurements of our microstructure. And this will involve very briefly something about how to align images, how to correct for illumination artifacts in the images, and then a bit about how to segment images, how to do interface characterization, such as surface areas and triple phase boundaries, and also at the end about how to characterize the network structures in the microstructure of electrodes. So this is the only slide about fuel cells. So very basically, a fuel cell, you have an anode side where you supply a fuel to, for instance, hydrogen in this case. Then you have a cathode side where you supply oxygen to. And then you have a dense electrolyte in the middle. And so you see here on the anode side, you have a hydrogen reaction with oxygen ions to produce water and free electrons. These can then pass through an external circuit here where you can draw flow from. And here on the cathode side, you have oxygens that are reduced by accepting these free electrons from the anode side. So the overall reaction is that you have the fuel, hydrogen here, reacting with oxygen to produce water and electricity. And in solid oxide fuel cells, this happens at very high temperatures, for instance 700 degrees. So that's all about fuel cells for now. Let's skip on to the more interesting parts. So this is the kind of data you get out of, for instance, focused ion beam tomography. So it's just an image showing kind of a data session where you have each frame in this video is actually one frame from the image acquisition process. And you can see here that, of course, due to the geometry of the focused ion beam setup, you have that the kind of rectangular region here that you would want to actually cut out to produce a cuboid of data that you can then further analyze that actually moves upwards in the image. And also you can see that there's actually a bit of shift here where kind of the whole sample looks a bit to the right image. So we want to correct for this. And to do this, we do a very simple line detection. Where we just detect fiducial line markers in the protected layer deposited on top of the sample. And by detecting this center line and also detecting the underline of the protected layer, we can obtain this intersection point on each of the frames. And we can then use this point here to align all our image data with. And you can see here, this is done on this modified sequence where you can see that this kind of point used here for the alignment is actually stationary in all the sequence now. So what we get out of this is a nice cuboid of image data where we have 3 dimensions, and at each location, each voxel location in here, which is just a 3-dimensional pixel, we have an intensity that specifies kind of the amount of electrons that we got back from that specific point in our microscopy session. And of course we can extract this cuboid data. As you might know from these focused ion beam tomography techniques, there's often a problem of non-uniform illumination across images because of kind of the trenches that we mill in our samples to get access to the data that we actually want to look at. This means that the same phase in the sample might not necessarily have the same intensity throughout the sample. And you can see this here, this is actually the same image, just color-coded in 2 different ways because it's a bit hard to see grayscale. But if you look at it here, you can see up here that this would be the nickel phase, that it actually has a high intensity up here than it has down here. This is of course not very nice if you want to do some kind of automatic segmentation of each phase in this structure. So we want to correct for this kind of intensity field we have in our image data. And I've used this quite simple iterative correction technique, where I pretty much just sample a large number of voxels randomly in 3 dimensions. So you can see this is just random samples on one slice through our cuboid, but it's actually taking place in the entire cuboid once. Then we fit a rigid hypersurface to the x, y, z and intensity data. And we fit a very rigid structure to not kind of fit to the local intensity changes to each individual phase. And we do this iteratively by fitting our hypersurface and then removing the samples that have the largest error compared to our fit in our hypersurface. And if we do this iteratively until a significant amount of these initial voxels have been removed, then we can obtain a fit of the intensity structure or the intensity change in our cuboid, and thus be able to actually correct for this intensity. So this is just an example of the correction. So you can see here these are images at different kind of image slices in our cuboid before the intensity correction. So you can see that we have high intensity here and the low intensity is down here. And by doing this correction procedure, we have a much more uniform distribution of intensities inside the same phase throughout our structure. And it is better exemplified by showing the before and after histogram of intensities. So if you look at the histogram of intensities in the entire 3D structure before this correction, you can see that there's actually no separation between the nickel and YZ phase here. But if you look at the histogram after correction, you're actually almost able to separate these 2 peaks. You're actually beginning to see that it consists of 2 peaks. And this will be very helpful later on when we try to do this automatic segmentation of our image data. So onto the segmentation problem. I'm sure most of you are familiar with this, what we want to achieve. So for instance, if we have an image like this, we want to be able to determine or interpret the image to figure out which part of this image actually belongs to each phase. I should say this is a quite low imaging quality structure. We have much better structures now, but this is just an example to show what we can actually achieve with these methods. So an image like this, if we want to segment the porosity, we might segment it something like this, which has been manually segmented. And so the general problem with segmenting these things is that you just want to do, for instance, a simple thresholding of intensities in a structure that looks like this. So you actually have high intensity areas inside, for instance, the porosity phase in places like this. Then if you just apply a simple threshold, then you will get both an under-segmentation in areas like this, for instance, where you don't get the full kind of extent of the porosity with you. And also at the same time, you will get fake kind of segmentation errors in areas like this, where you have a low intensity over here, which is not actually a porosity structure. So we want to, we're developing a method for actually trying to segment these image data with artifacts like these in them. So here I'll just go on to actually show the result before I actually explain what's going on, just to give an idea of what it is we are trying to do with this methodology. So the general idea behind this is that we want to seed our initial segmentation in the regions that have very low intensity, which we say this corresponds to porosity and very high probability. And then from these initial seeds, we then want to evolve our interface such that it passes over the areas of our structure that we say belong to the process phase, and also that it stops at the interface boundaries in our volume that we would say are actually true interface boundaries to other phases. So I'll just go back to basics and actually try to explain how this is actually being done. So this evolution of these interfaces is done using something called implicit interfaces. So what we do is that, for instance, this is a 2D curve representation. So if you want to represent this curve, for instance, you can represent it by a certain level set of a distance function. So for instance, if you want to represent this interface here in white, then you have this kind of